mathematicians. Today we're going to start a chapter over systems of equations. So before we get started, we need to know what a system of equations is. So let's start with the definition of system of equations. A system of equations is simply a set of equations with the same variables. Most of the ones we're going to be starting with, as far as just flat out learning how to solve them, the methods to solve them, they're going to have the variables x and y. When we start solving some practical applications, our variables are going to change due to the situation of the word problem. But as far as the definition of system of equations, this is what we need to know. Okay? Today we're going to be graphing to solve. So to graph a system of equations, you simply graph the equations on the same coordinate plane. Okay, if the system contains two equations, you graph both equations on that coordinate plane. If it contains three, you graph all three. You get the picture of that. Okay. Next thing we need to talk about is the types of solutions we're going to run into. There are three types of solutions to a system of equations. The first type is a single solution. Okay, now think about this. The solution to a set of equations is the point of intersection of the two equations, or the graphs of the two equations. So as you can imagine, a single solution is if the lines cross in one place. Okay, so if it has a single solution, you're looking for the ordered pair at the intersection. Okay, so the lines intersect at exactly one place. All right. There's also a situation where you run into infinite number of solutions. Okay, now infinite is different than all real number solutions that we've had before. It's not saying all real numbers, it's just saying that there is an infinite number of solutions. And what this looks like is when the lines are actually on top of each other. Okay, it's actually the same, when you simplify the equation, it's actually the same equation when you graph it. And the lines are on top of each other. That means every ordered pair on those two lines, which are on top of each other, so it's basically the same line, every single one of those ordered pairs is a solution. And it's infinite because, as we know, those lines go on and on and on in both directions. Okay? The last type of solution would be no solution. All right? Can you think of a situation where you've got two lines on a coordinate plane and there is no point of intersection? What are those going to look like? You've got it. Okay? You know what they are. They're going to be parallel lines. Okay? So a no solution is when there are parallel lines. One solution, the lines intersect at one particular point. Infinite solution, it's basically the same line. The lines lay on top of each other. No solution is when you graph those equations and they are parallel lines. They will never intersect. Okay? If you take a look at this, there's some terminology that we're going to use throughout this. And if there's exactly one solution, it's called consistent. Okay? Consistent means that there is at least one solution. And actually both one solution and infinite solutions are both called consistent because they do have a solution. Okay? Exactly one solution is also called independent, okay? Because there is only one solution, so it would be considered consistent and independent, okay? Infinite solutions is consistent because there is at least one solution, and it's called dependent because those lines are laying on top of each other. For a no solution, okay, which are parallel lines as you can see, we call it inconsistent. If consistent means there's at least one solution, inconsistent means there's no solution. So we can stop and you can look at those and get those copied down as you need. We're going to work three examples today. Here's our first system of equations. And if you can see one of them right here, we can already go ahead and graph that. So let's get that out of our way. As we know, if it just says y is equal to a number, okay? That means that it's a horizontal line because it has zero slope. That's what happened to x. We multiplied it times 0, it's gone, okay? So that means we're gonna have a line that crosses the y-intercept at -2, and it's horizontal. So let's go ahead and get that line on there right now. And I'll make it red since the equation was in red. We go down 2, so our line is gonna cross. This is what our line is gonna look like, okay? I'll try to get some arrows on it so you guys won't hound me about it, okay? So there we've got our first equation graphed, right? We need to do some work on that second equation, so let's move this down out of the way. We need to solve this for y, get it in slope-intercept form, so we can graph it. Our first move would be to subtract 3x from both sides. And when I subtract 3x from both sides, this is going to cancel out. I'm going to bring down the negative y is equal to negative 3x minus 1. They're multiplying y by the ghost of -1. So we're going to divide every term in here by -1. Basically, all that does, we've learned, is it changes the sign on each one of the terms. So now we have y is equal to 3x plus 1. So to graph this one, we're going to start at +1 on the y-axis. It has a slope of +3, which means we would go up 1, 2, 3, and over 1. Okay? We could also go down 1, 2, 3, and 1 to the left. Well, looky there. Look at that point where it's at. 1, 2, 3, and 1 to the left. All right? So when we graph this line, let's make it a nice blue line to match our equation so we keep things straight. It's going to come up and it's going to go right through here. And if you notice, we have a point of intersection. Okay, forgive me on that one. Okay, we have a point of intersection, and that point of intersection is right here. That ordered pair is a solution to both of our equations. If we plug them in, we'd get true statements on both of them. So this ordered pair is -1, -2. So the solution to this equation is -1, -2. -1, -2. Okay? And if we plug those in, it's going to work. If we plug y in here, -2 is equal to -2. If we plug in both of these here, this would be -2 is equal to 3 times -1, which is -3, plus 1, which is -2. -2 is equal to -2. All right? Let's take a look at this next example. All right? The first one's in slope-intercept form for us, so let's just go ahead and graph that one. Has a y-intercept of 3, so we will start out at 3, 1, 2, 3. It has a slope of +2, so I can go up 2 and 1 to the right, or I can go down 2, 1 to the left, down 2, 1 to the left, down 2, 1 to the left, and down 2, 1 to the left. Okay? So, as we're here, let's go ahead and get that line on there. We'll make it blue to match our color scheme here. And so that one, so we can start right here, and we'll draw that line up through here. All right? I'll go ahead and put our arrows on it here. Okay, and let's get rid of that. There we go. Okay, so now we've got this one. It needs some work, like the other one did on the last problem. So we're going to need to subtract 8x from both sides. That's going to leave us with -4y is equal to -8x minus 12. Since we're multiplying y by -4, we need to do the inverse of that and divide everything by -4. When I divide it by -4, I end up with y is equal to 2x plus 3. Look at this equation and that equation. When we graph the two, they're actually going to be on top of each other. So let's go ahead and get that. So it has the same y-intercept, it has the same slope, so it's basically the exact same line. And if we look at this, as we go over that, we see that it is. It's right on top of our other line. So this one would be considered consistent and dependent, all right? Infinite number of solutions. All right, bear with me. One more example. I want to give you an example of each type. All right, on this one, we've got to do work on both of our equations, so let's get some room so we can do it. On the first one, we're going to need to subtract x from both sides. That leaves me with negative 2y is equal to negative x plus 4. We need to divide by negative 2 all the way across. That's going to leave me with y is equal to 1/2 x minus 2. So let's go ahead and graph that. We have a y-intercept of negative 2. And we have a slope of up 1, 2 to the right, up 1, 2 to the right, up 1, 2 to the right. Or we could go down 1, 2 to the left, down 1, 2 to the left. So let's go ahead and get this line on here. Let's see, let me start here. When I draw this line through here, okay, let's get some arrows on it. We've got our graph of that line. Now let's go ahead and solve the second equation so we can graph it. Again, we need to subtract x from both sides. That cancels out, leaves us with negative 2y is equal to negative x minus 2. All right. So now we've got to divide everything in there by negative 2. That's going to leave us y is equal to 1/2 x plus 1. Look at these guys, if you will. What do we know about parallel lines? What did we learn about parallel lines? Exactly. They have the same exact slope. This one had a slope of 1/2. This has a slope of 1/2, which means they're parallel lines. Let's go ahead and graph it so we can get a visual on it. But it has a y-intercept of positive 1. It has a slope of 1/2, which means I go up 1, 2 to the right, up 1, 2 to the right. Or we could go down 1, 2 to the left, down 1, 2 to the left. And if we graph that line, I think it's going to give us a visual that they are actually parallel lines. And we know that parallel lines never intersect. So So we've got our two lines there. They have the exact same slope, 1/2 and 1/2. They have different y-intercepts. So in this case, there is no solution, and this would be considered inconsistent. I hope this helps you a little bit, and I'll see you next time.